Hi, I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University. This lecture is going to cover some questions and answers associated with Chapter 2 out of Tinoco's book, Physical Chemistry, Principles and Applications in the Biological Sciences. So I have a separate video that overviews the material covered in this chapter. We'll also be covering several problems as well. This video is just going to look at several things over the course of giving lectures on this material that students have generally had questions on, and some answers to those questions associated with Chapter 2 in this book. We'll have separate videos that go through very specific example problems and etc. A lot of the questions that has arisen from this chapter come down to understanding for the first time, heat processes in thermochemistry. And really the key concept that's introduced in Chapter 2 associated with heat is the enthalpy. Now, as I've stated before, Chapter 2 is really a review of a lot of material that you've already seen in introductory chemistry and physics courses. So what are we really trying to do here? Well, there's one very obvious thing, which is we're taking some of the thermochemistry, thermodynamics we learn and we're applying it directly to problems and the science in biological systems or biochemistry. But there's a couple other things when we bring back around thermodynamics that we're going to do at the same time. One is we're going to really try to look at it from a more mathematical calculus basis. And really, you can summarize thermodynamics as the mathematical exercise of looking at things as far as partial derivatives. It's looking at the derivatives or the change in each of these energy functions or work and heat functions and looking at them systematically, independently, one at a time through their partial derivatives. And so really it's an exercise in partial derivatives mathematically. So we want to really emphasize that higher level of mathematics because it gives us a much deeper understanding of the subject, the fundamental field. So that's one goal. The other goal is really, as chemists, biochemists, et cetera, in physics, we really want to have kind of a bottom-up approach to thermodynamics, or really try to understand it at kind of a molecular level. So that's another goal of this, is not to just look at the macroscopic outcomes of thermodynamic principles, but really try to build it up from kind of a microscopic or fundamental molecular understanding of the material. So when we look at thermochemistry and introduce heat as it's associated with enthalpy, which we've seen several times in introductory chemistry and physics classes before, we really want to take that approach. So, for example, we often just in introductory chemistry talk about enthalpy in fairly general terms, and oftentimes the enthalpy is associated with the heat. But let's make it very explicit what we're talking about, under what conditions. And it's really under isobaric conditions or under constant pressure conditions. So why is that? Well, I always start almost any thermodynamics problem back at looking at the first law. And so whether you're looking at it in kind of general terms that you see, just that it's the change in the work and the heat. Like I said, we're going to look at this at more of a calculus level. So I would say that this is the change in internal energy is the change in heat plus the change in work. And the reason I've put, work here, lines here is to represent that these are path dependent, and this is an exact differential that is path independent. It's a state variable that only depends on the initial final states, while the change in the work and the heat can be path dependent. They're dependent on the path in which you take them. And this is kind of a general statement of the first law. What I like to think of as the combined first-second law is to put terms to what the heat and work is. So in very general terms right now, Chapter 2 spends a lot of time defining the work functions. So we can look at these works as the force, derivative in an x variable or a length of some sort. A lot of people would call this the length. This force could be mass gravity, and the change in the length or the x could be the height. That's one that gets looked at a fair amount. You could look at this from a two-dimensional surface tension, surface area type thing, or 3 dimensions, which is where I say we end up most of the time, which is the external pressure into the change in its volume. Right? And this is really, when we look at gases, which ideal gas law, gases is often where we start looking at thermodynamics in introductory chemistry, and again in this course as well. And then we look at chemical work, the chemical potential, how it changes with the number of moles, right? And so this is really what we get to, kind of in later chapters. So initially, we often look at problems where it's a closed system, a fixed number of moles, etc. And then we're going to introduce in chapter 3 really what heat is, and because we've already had this before, I think it's appropriate to remind us that this is going to be the temperature, the change in entropy. But for now, in chapter 2, we're really just focused in on generalities of heat, which we'll explore through the second law in the next chapter. So like I said, initially, we're going to often look at gases or phase changes to define this. So we're not going to be introducing any chemical reactions. So we're not going to change the number of moles. We're not doing this at different heights, gravitational fields, et cetera. And we're not looking at one-dimensional systems like we did early in the chapter with, for example, the atomic force microscopy. And we're going to stay kind of just in general heat terms. So, we would say in this case that the internal energy, which is the change in heat, and then oftentimes the work is the external pressure into the volume. So if we want the change in heat to be associated with the change in energy, then we do that under constant volume conditions, which is a way of just saying that there's no change in work. But if we think of what we're doing with gases, with phase changes, when we look at a lot of these initial things, it's not convenient or common to do things at constant volume. It's much more common to do things under constant pressure, under atmospheric 1 atmosphere pressure, or under an isobaric conditions, where it's the change in pressure that's 0. Well, and then once that's true, and therefore the change in work will go to 0, and the change in heat is all you will look at, and that's under constant pressure conditions, and that's where the energy associated with that is the enthalpy. So, and since the heat capacity is defined as how the change in heat with temperature under whatever things are constant, so the constant pressure heat capacity is that, and under constant pressure conditions, that's associated with the enthalpy. And again, we're always looking at this from the system standpoint with if work is released by the system, it's negative, or if heat is given off by the system, if heat is absorbed by the system, it's positive. And we can see that we expect the enthalpy to be higher than the internal energy because it's adding this additional PV term to it. Now, that's a fairly general way. Like I said, we really want to focus in on some of the mathematics of what makes this possible, and really what that's looking at is Legendre transforms. And so I give you a couple places. Your book doesn't cover this in a ton of detail, Tinoco, but Wikipedia does if you look up Legendre transforms. A lot of different physical chemistry textbooks, one of my favorite is Berry, Rice, and Ross, covers this fairly extensively. But we'll look at it in this one case, and this really generally applies to a lot of different energy terms. So as we said, like the enthalpy is defined to be U plus PV. And we're going to show that this is, in a sense, a Legendre transform, that what this does is the enthalpy is an energy just like the internal energy is. So why switch to this other type of energy? It's because it has different dependent variables. The internal energy is dependent on heat and specifically on the entropy. the work, the pressure volume work, it's dependent, it's on the extensive variable volume. If it's not a closed system, it's dependent on the number of moles, right? What we're going to show is that the enthalpy, in a sense, is dependent on the same variables, except not the volume, it's dependent on the pressure. And this is the key thing, is that we're looking at same types of energy, but different dependent variables that it's associated with. So, like we said, we know that the internal energy is heat, minus PdV, and then if we added this for this term, just to be clear, it would be the sum of mu I dni. So it's dependent on N, V, and in this case, this is T ds. So there. So how does the enthalpy change these variables? Well, if we take a derivative of this, then that's du plus the derivative of the product PV. Expanding that, du is plus PdV plus VdP, chain rule, in calculus. And like we said here, this is the heat term minus PdV plus PdV plus VdP. So these two go, and then this is dq is plus VdP. So, and like we said, this would be entropy. This is TdS. If it was dependent, if you change the number of moles, I left that off right here because it would just stay the same through here. But really what this did was change our dependent variable from volume to pressure. So now if we say that we're under isobaric conditions, which is dP is equal to 0, or if you integrate that, delta P is equal to 0. This is 0, so this is where we get the term that the change in enthalpy is just the change in heat, or dH is equal to Q, as we would write it. So that's what gets us to this statement right here. And that is a Legendre transform from the internal energy to a different type of energy that has different dependent variables. This, just to give you a sense where this goes, this is how we, the Gibbs free energy is the same thing. It is U plus PV minus TS, so it's a double Legendre transform to get. So we look at several different energies. The Helmholtz free energy is defined to be U minus TS. So we can go from different types of energy, whether it be enthalpy, Gibbs free energy, or sometimes the internal energy, depending on what natural variables are most convenient for the problem. And so that really is what gets us to why Legendre transforms are so important. And you'll even see there's a whole section on thermodynamics and Legendre transforms for Expedia. Now, once we have that, so now we know that why is that? So under isobaric conditions, the change in pressure is 0. So what we're often doing is, what we're saying is we often do biochemical thermodynamics, at atmospheric pressure, right? We typically do things at, 1 atmosphere, and we don't change that. We do it just on the benchtop, et cetera. So this is a very convenient variable for biochemistry. And under those conditions, the change in enthalpy is the change in heat. And so without knowing anything about the molecular nature of heat, at the moment we can still associate it with this energy. And so a lot of the book, the rest of the chapter after it introduces enthalpy, shows how practically it is. And one of the first things, in fact, this is done in numerous problems. So in chapter 2, at the end of the book, or end of the chapter, problems, in problems number 6, 11, 12, 13, and 20 are all based on problems that have to do with just water. And it's not water undergoing chemical reactions, it's typically just undergoing phase changes or changes, work and heat type changes to get a sense for this. But as you can imagine, this is a very practical process. Often when we melt ice, when we evaporate water, etc., we're doing that against a constant external pressure of 1 atmosphere or under atmospheric pressure. So it's the enthalpy that really gives us a sense for how the energy in this system is changing, and that we're not doing any work, and we can look through the enthalpy at how the heat is changing, or how heat energy is being taken up or absorbed or released by the system into the environment, or vice versa, right? And so just to remind us, you know, when we talk about, we start at cold temperature, we have solid crystalline H2O, ice, in a certain crystal structure, and then we can melt that into liquid water and then evaporate that into steam or vapor. And there are, I mean, a lot of terms for this, right? We often call this steam or vapor. Liquid, we just mostly call this water. You know, solid H2O or ice. This process right here, if we look at what the energy is and we do it under constant pressure, then the relevant variable is what is the change in enthalpy, which is telling you what is the change in the heat during that process. And instead of calling it the delta H of melting, it's typically called the delta H of fusion. And it's because it's a solid fusing into the shape. So it's the enthalpy of fusion. And the reverse of that, which you could call freezing or crystallization, because it's a liquid that is turning into a crystalline lattice structure, solid structure. So there's several terms you can use, but we generally, it's equal and opposite. So this will be the minus delta H of fusion, which we often do that. Evaporation, we often just do this as vape, so we'll just do delta H of vaporization. And this, the condensation reaction, is minus that. And then, of course, if you add these two together, you go directly from ice to the vapor. That would be the delta H of sublimation. If you go directly from the vapor to the solid, that's a deposition. So that gives you kind of some general sense. So often what you see in tables are the delta H of fusion. They rarely give you the reverse of that, in a sense, the delta H of crystallization or freezing, because by giving you this value, you know that if you do it at least under equilibrium conditions, that it's just gonna be the negative of that it's just the reverse. Instead of absorbing heat into the system to melt, you're gonna release the heat so that for it to crystallize or freeze. And then instead of absorbing heat into water for it to evaporate, you're going to release heat from the vapor so that it can condense. And this is really one of the most useful, when Gibbs himself even wrote several papers on basically visualizing or graphically representing thermodynamics and its problems. And I find this to be one of the most useful ways so that you can really look at what's going on. So I grabbed some values, and in fact I grabbed them from table 2.2 in your book. I grabbed the molar enthalpy of fusion here. I grabbed the heat capacity. I grabbed the heat capacity of water and the molar heat capacity for the vapor and the vaporization enthalpy. So this is 40 kilojoules, this is 6 kilojoules, etc. So I grabbed those values and put them here just so we can see how those values translate. And so what this is taking is it's the molar enthalpy at some value, and it's in a sense versus subtracting away the standard state. So at 298 is where that'll be 0. And so this is just scaling it to the standard state enthalpy of the system. And it's doing it in kilojoules, so that's why I've taken this into kilojoules here. So really what the heat capacity is giving you is how the enthalpy changes with temperature, and this is at constant pressure. right? So it's giving you this slope, right? And we can even see that, like that for ice, you have a specific slope here. And because the heat capacity is larger for water, roughly, a factor of 2, the slope is a factor of 2 more. And then it goes back to about the same, for steam, right? So this is, ice, this is water, and this is steam. And you're absorbing heat, on each of these processes to get one from the other. For example, if you're given a problem where you're starting, at ice and you're asking how much, heat is required to get, to melt ice and get it up to room temperature, you can look at that process in steps. You can take, you'll go the heat capacity, the change in temperature from, say, whatever temperature you're at to 0. Then you'll take the delta H of fusion, because this is the heat capacity, this is the delta H of, say, step 1. The delta H of step 2 would be to take that ice and melt it. So basically to take the delta H of fusion, and then maybe step 3 by Hess's law would be to then take that liquid water and warm it up to whatever final temperature you want. And by adding those 3-step enthalpies together would give you the overall enthalpy of a process of taking ice at, say, -20 up to liquid water at room temperature. And that is associated with one of the problems. You can also scale taking a problem like taking water, I think, at a specific temperature and mixing ice in with it. And so you can often do that, in an adiabatic container where the overall change in heat or change in enthalpy is 0. So any heat lost by the water must be or absorbed by the ice must be lost by the water. So the water temperature will drop, the ice temperature will increase. It'll start to melt through that process of fusion, of basically melting the ice. And you'll end up with water at 0 degrees mixed with water at a temperature. And of course that thermally isolates as well till you end up with a cold water sample. Or you might end up with a sample where it's a mixture of ice and water, and you can determine exactly how much of the ice melted to get the water down to 0 degrees. And then you have a mixture of ice of water at 0 degrees and ice at 0 degrees. And you can figure out how much of each the final state would be. So I would encourage you a lot to look at both phase changes, and just, changes in, gas structure of CO2 and different things under constant pressure conditions as a good way to get an initial feel for enthalpy. And water is most commonly used, but it's very instructive to take this same type of diagram and instead of water, change it up and look at the, melting or evaporation of different biologically relevant compounds to get familiar with this process and get a feel for what enthalpy is. So I hope this helped with some of the major questions associated with some of the mathematics behind understanding enthalpy and the Legendre transform, and using that enthalpy in some of the problems to better understand heat processes and thermochemistry for Chapter 2 in Tinoco. I'll follow this up with some explicit examples from the end of the chapter of Chapter 2 in Tinoco. Thank you.